The metadata serialization engine provides standardized conversion of in-memory object representations to persistent byte sequences. The system operates at the serialization layer, between application memory spaces and storage backend interfaces. Core functionality includes type marshalling, field ordering, and byte-level encoding protocols. The engine maintains strict format versioning to ensure backward compatibility across system versions. All serialization operations are stateless and deterministic. Schema definitions are declared using a declarative markup language embedded within configuration files. Each field declaration specifies its type identifier, byte offset within the serialized record, and nullable status. The schema parser validates field ordering at initialization time, ensuring sequential byte alignment. Primitive types include signed and unsigned integers of varying width, floating point representations, and fixed-length byte arrays. Complex types are decomposed into nested primitive sequences. The encoding phase transforms object field values into their binary representations. Integer values use 2's complement notation for negative numbers. Floating point values conform to IEEE 754 double precision standards. String data is prefixed with a 4-byte length field, followed by UTF-8 encoded characters. Boolean values occupy a single byte. Null values are indicated by a reserved marker byte within variable length records. Deserialization reconstructs in-memory objects from byte sequences by reading the schema definition and extracting fields at their declared offsets. The deserializer validates record length against the expected size derived from the schema. Out-of-bounds reads are detected and raise an exception condition. Field extraction proceeds sequentially from offset 0 to the final declared field. Type conversion is implicit and follows the declared field types. Version compatibility is managed through schema evolution rules. New fields are appended to the schema with a version marker. Older records lacking new fields are handled by applying default values. Removed fields are deprecated through a transition period where they remain in the serialized format, but unmarked. Field type changes are not permitted. Migration utilities support bulk conversion of existing records to newer schema versions. The compression subsystem optionally reduces serialized record size through standard algorithms. Deflate compression is applied to variable length fields exceeding a configurable threshold. Compressed payloads are prefixed with a compression flag and original length. Decompression occurs transparently during deserialization. Compression ratios vary based on field content and type distribution. The compression overhead is typically recovered for records exceeding 2 kilobytes. Checksumming provides integrity validation for serialized records. Each record concludes with a CRC32 checksum computed over all preceding bytes. The checksum is stored in the final 4 bytes. Deserialization validates the checksum and raises an error condition on mismatch. Checksums detect bit-level corruption from storage media failures or transmission errors. Checksum computation is performed once at serialization and once at deserialization. The field registry maintains mappings between symbolic field names and their offset positions. Registry lookups are performed at initialization and cached in memory. Dynamic field access through symbolic names involves a hash table lookup, followed by offset calculation. Direct positional access bypasses the registry and reads directly from computed byte offsets. Registry entries are immutable after schema compilation. Field name collisions result in a compilation error. Binary padding is automatically inserted between fields to maintain byte alignment on processor boundaries. 8-byte fields are aligned to 8-byte offsets. 4-byte fields require 4-byte alignment. This alignment reduces the number of instruction cycles required for field access on most architectures. Padding bytes are 0 during serialization. The serialized record size is calculated as the final field offset plus its type width. Array fields are serialized as variable length sequences with a 4-byte element count prefix. Each array element occupies a fixed width determined by its type. Multidimensional arrays are flattened to single-dimensional sequences with row major ordering. Array deserialization allocates memory proportional to the element count. Empty arrays are represented as a 0 count with no following elements. Array bounds are enforced during deserialization. The indigenous layer handles byte ordering differences across processor architectures. The system defaults to little endian byte order for all multi-byte fields. Explicit indigenous conversion functions are available for big endian systems. Indigenous is determined at runtime during engine initialization. Records serialized on one architecture can be deserialized on another without manual conversion if indenness is consistent. Object references within serialized records are handled through pointer encoding. Direct memory pointers are not preserved. Instead, references are encoded as global object identifiers that are resolved during deserialization. This approach ensures portability across process boundaries and persistent storage. Reference resolution occurs lazily on first field access. Broken references result in a null value or exception, depending on the field's nullable status. Nested object fields are serialized as embedded records within the parent record's byte sequence. The nested structure maintains the same schema rules and encoding as top-level objects. Nested objects do not introduce separate length prefixes. The parent schema declares the nested object's type, allowing the deserializer to extract nested fields at their calculated offsets. Deeply nested structures are supported without practical limit. The streaming serialization mode processes large objects incrementally without loading the entire record into memory. Field data is written to the output stream sequentially. Streaming mode is suitable for objects exceeding available memory. Checksumming and compression operate on chunks rather than the complete record. Deserialization can pause at any field boundary and resume later. Streaming introduces minimal computational overhead. Schema migration utilities provide batch conversion of existing records between schema versions. The migration process reads records under the old schema and writes them under the new schema. Default values are applied to fields that did not exist in the old schema. The migration is idempotent and can be re-executed without side effects. Progress tracking is maintained for large batch operations. Performance characteristics of the serialization engine are deterministic within predictable bounds. Serialization time is linear in the number of fields. Deserialization time is similarly linear. Memory allocation is proportional to the record size. No dynamic resizing occurs after initial allocation. The engine is suitable for real-time systems where latency is critical. Benchmarking results are available in the performance appendix.